Alright, recording is rolling. It is Thursday, November 9th, which is the last day of this week because tomorrow is Veterans Day. Veterans Day. We're going into a 3-day weekend. Right, so we are going to finish this half page, this momentum half page, which is just some basic momentum questions. Of course, like with a lot of these questions, you guys could just take the equations and turn your brain off and plug and chug and get all the answers just over, right? But a lot of these too, what I like to do is to give extension questions. Maybe play around with variables. What are some proportional type questions, or what if you like change some detail? How would that change the question? So we'll do things like that too. Then we'll move on to your guys' textbook puzzles. That's chapter 6. We'll get a good start on these today, and we'll continue these next week. You guys remember AP Classroom? Been open for a few days. Let's have this due on Monday. I did, guys, opened up this morning just to check. I got a notification from AP Classroom, said that AP Classroom is going to be down for maintenance this Saturday and Sunday morning. So I do recommend that you try to knock this out maybe on Friday, because your next best opportunity might be Sunday evening, which is kind of okay. So sorry, I didn't know about that till just this morning. So okay, great. I think you guys will be able to handle that. But heads up about that. All right, we got some rocket launches coming up. There's one in a few hours. So around 8:28 tonight. You guys watching the sky? Reports north. Right, and then Saturday, Sunday, got a couple of rocket launches. All right, well, I'm doing announcements. Got one from Mr. Dravies. Mr. Dravies, Powder Puff meeting. If you're interested in this, there's a meeting Monday after school in the media center, which of course is the next school day, but it's not for a few days because 3-day weekend. Right. So if you're interested in Powder Puff, then Monday after school in the media center with Mr. Dravies. All right, let's get going on this momentum half page right here. Momentum. All right, so we've done most of this. We got types of collisions, we got general momentum, we got perfectly inelastic, which was like your guys' lab yesterday. We got a grenade exploding. I think we did do elastic, right? I just didn't circle the answer, right? So perfectly elastic. Right, you guys remember? I gave you guys system of equations between conservation of momentum and also conservation of kinetic energy is what's unique to perfectly elastic. That's like perfectly bouncy, right? Think like Newton's cradle. Right? Okay. I told you guys in terms of AP exams, AP, if they ask a collision question, it tends to be inelastic rather than perfectly elastic because the math is a little bit crazier on that. But anyway, okay, that's how that works. Right, so I think we're ready for number 8, right? We're ready for number 8. Right, now number 8, number 9, both involve coefficient of restitution, like how bouncy is some type collision. Right? Number 8 is more in terms of the definition. Right? So we got two objects, object A and object B. I gave you an initial and a final velocity on each one of those. Right? What's the coefficient of restitution? So if you look at the definition of coefficient of restitution, that's just the fancy physics way of saying how bouncy is a collision. Right? What you're looking at is post-collision difference in velocities, right, compared to pre-collision difference in velocities. Right? Just divide that. It's going to come out of some ratio. If the two objects stick together, then what is the post-collision difference in velocity? 0. Therefore, coefficient of restitution would be 0. Right? So that's one boundary condition. The other boundary condition is what if these were like perfectly elastic, like as bouncy as it could possibly be, and then kinetic energy is also conserved, blah, 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 right? What does this come out to be? Like 1.000, right? So realistically, this number is usually somewhere between those two, right? Between 0 and 1. Okay. Let's see what it is for this case. Right? Notice I did not actually give you the masses of the objects on number 8, right? Which you don't actually need to figure out how bouncy this is. Right? It's kind of a material property, right? It's like if you bounce a ball off a carpet floor versus a tile floor. It's like, well, it's like the same mass objects at play, just maybe they bounce a little bit different. Right? So I get coefficient of restitution is, right? Now if I do V, velocity of object B final minus velocity of object A final, right? Got the post-collision difference of velocities. Final is like post-collision, right? Compared to, now if I write it this way, velocity B initial minus velocity A initial, at a glance it looks completely logical to write it that way, right? Because it's like, okay, final over initial, B minus A over B minus A, right? But whenever you have a collision, you usually have some kind of reversal in direction. If you plug in the numbers exactly like this, you'll always get a negative number. Is what I'm trying to get at. And there's a few ways around that. You can take absolute values. You can reverse a couple of these. Like instead of B minus A, you could swap one of these A minus B exactly like down on this poster. Or I can just slap a negative sign in. Right. So do one of those things. So it'll force that to always be positive. Right. At this point, we can just plug and chug. So I'm just gonna go and do that. So I got VB final. I'm just picking the numbers straight off my page. Looks like it rebounded at 2 meters per second. At VA final on my paper, I got 3 meter per second. Right. Right. And then VB initial, I got 0 meter per second. Okay, so maybe on my paper anyway, it looks like object B was just sitting there at rest, just kind of like that. And then VA initial, I've got -9 meter per second. Okay. So if I attach a story to my collision, it looks like object B was just sitting there, object A was coming in at a negative direction and bam, slammed into it. And then object A like rebounded, right? And then object B was pushed back to the left, right? Now, even though I didn't give you mass numbers, you can look at this and pretty well figure out, it looks like my mass A is relatively small and my mass B is relatively large mass. I mean, that could be its own fun question, right? What's the ratio of the masses of these things, right? That maybe it's a little tougher, right? Slap a negative sign on this to turn it positive. Let's see what I get. 2 minus 3, it's -5. 5, cancel out that negative, divided by 9. 5 over 9, boom. Okay. So 0.56 about. Okay. This is a unitless ratio, or you could say meter per second over meter per second. Right? So it's just a number. Right? But you don't see too often in this class. I guess anything that starts with like coefficient of, right, doesn't really have a unit attached to it. Okay. See a number, circle that. Boom. Remember, coefficient restitution bounded between 0 and 1. This is pretty close to half, so it's kind of halfway between those two extremes, right? Oh yeah, go. It's how bouncy is a question. Yeah, how bouncy, right? So if this number was 0, that means the two objects stick together because they have 0 difference in velocity post-collision, right? If this number is 1, that would correspond to like a perfectly bouncy situation, like as bouncy as you could possibly get, right? If it was somehow bigger than 1, then the only way for that to happen is if there was like energy added during the collision, or maybe it could be an explosion, possibly something like that, right? You have to have energy added, right? And this, okay, so this looks a little more bouncy than not, but it's kind of halfway in between. Right, now, number 9 is the same question, what is coefficient restitution, but it's from a little bit different perspective. Saying, what if you drop a bouncy ball and it has a drop height and a rebound height? And so, boing, which I do also have a poster for. Right, so here's the main definition for coefficient restitution, right? Something about right, this ratio, right? But here's a different perspective on it. I do want to have you guys do this lab next week. It's a real straightforward lab, right? It's just you drop a ball and then measure how high does it rebound to, right? So how does that fit into say like this context that we just did for the last question, right? Well, the two objects colliding here are the ball itself and the entire Earth, right? And since the whole Earth relative to the ball is basically not moving, we're going to treat it that way, right? Relative motion, right? Then we can say the difference in velocity between the two objects is just the velocity of the ball itself, right? Because anything minus 0 is just the velocity, right? So I got a crash speed and a rebound speed. Now, it might be kind of hard to get what those speeds are. I mean, I guess you could fix the speed gate in just the right position and have it on the way down, have another one on the way, okay, that here. But you know what's a lot easier? It's just to pull out a meter stick, say, well, what's the drop height, what's the rebound height, and to calculate what those speeds are, right? Because you guys know what that is, square root 2gh, which you guys have seen, probably at least a dozen times by this point, right? So you guys saw that back in kinematic days. You guys saw it more recently with conservation of energy, right? Galileo drops the ball, potential at the top, kinetic at the bottom, right? And it was always this, right? So speed at the bottom is square root 2gh, right? As long as you drop it, as long as you don't throw it, okay? Right, so that's true for dropping and for rebound. I got the rebound height here. I got the drop height here. And so if you divide those two speeds, see like the 2 and the g is going to cancel. So it just boils down to this, right? So you take the ratio of the heights, right? And then the square root of that represents coefficient of restitution, how bouncy it is. So that's all we got to do is just plug in those numbers just like that. So go number 9. Coefficient restitution is, well, I know it's something to do with, I'm going to backtrack a little bit, square root 2gh over square root 2gh, right? Because that's ratio of the speeds, the 2g goes away, right? I'm getting the square root of ratio of the heights. Now my heights, let's see, I dropped it from 1 meter and it rebounded to, halfway up, 0.50 meters, okay? As long as you're consistent in your units. If you do meters and meters, or you do centimeters and centimeters, as long as it's the same unit, then you'll always get the same number. Okay? So if it bounces halfway up, how bouncy is that? Okay. I'm looking at Ooh, about 0.71 it rounds to, right? So it's about 71% bouncy is what that is. Right? So rebounds with 71% of its crash speed. Okay? We'll bounce up to halfway mark. All right. Oh, it's right there. Circle that. All right, you guys good? Right. I think I mentioned before too. I've never seen AP ask a question on this concept, coefficient restitution. Right? So if they did, they'd have to set that up in the explanation and say, okay, well, here's what this is, and now you can go ahead and blah, blah, solve something. Right? But I doubt they will because I've never seen ask that before. Okay. Last couple questions are the same story, the same premise, has something to do with like a baseball bat hitting the baseball, right? And then I give you different variables and say solve for different things. Okay. So number 10 says bat hits a ball with some force for some time interval. Right? Here's the mass of a baseball, right? What's the change in velocity of that baseball? Okay. So both these last two questions, here, it's this right here, impulse, right? So impulse is a change in momentum, right? That's just a physics term for that. And it's some force for some time interval. This graph right here, force versus time, you will see such a graph on the AP exam. You might see several graphs that look for force versus time. Anytime you see a force versus time graph, the first thing I'm thinking, the gears are turning in my mind, is I'm thinking, okay, something to do with an impulse or something to do with the momentum transfer. Okay? Now this looks kind of similar to something that you guys saw last week. Right? Last week, you guys saw force versus distance graphs. What if you push with a force for some distance? That was a transfer of energy, and the physics term for that is called work. Right? This is a similar type concept. Right? It's usually involved in collisions. Right? So momentum transfer during collisions. Right? Force versus time. Right? Also, my poster examples for work, I gave a constant force, so it's a rectangle shaped graph, right? But for impulse, it's very common from a textbook to see triangle shaped graphs, right? Like with a variable force. Now, why would that be, right? So I'm hitting this ball with this bat. It's supposed to be filmed this in slow motion, like 1,000 frames per second. Here, the bat makes contact with the ball. The bat pushes, right? Slows the ball in, right? At this point, now the ball's turning around, right? Start to rebound away from the bat. And at this point right here, the ball loses contact with the bat, flies off. Right? Now, there is some associated average force. If you do average force times time interval, okay, that's the impulse, that's the momentum that you transfer to the baseball, right, which represents mass times change velocity of baseball, right? Same thing, force times time is mass times change velocity, right? Again, notice that's average force, right? So the area of this rectangle is the same thing as the area of that triangle to represent impulse, right? So let's look at the numbers on this one. Right, number 10, of course, my numbers are different than your numbers, but same story. All right. And the picture is just this picture right here, right? That picture is this question. So I got mass times change in velocity of the baseball comes from applying an average force for some time interval. And I gave you 3 of those 4 variables. So just solve for that right there. Right? Hey, let's solve this in terms of variables. That's a good thing to do, right? You can do that in one step. Right? You got average force times time interval, and then divide by the mass of the ball. That'll tell you how fast change of velocity, right? Right. Ooh, I see some proportions here, right? The more force, the more it changes. The more time for the force, the more it changes. Right? The more mass of the ball, the less it'll change what it's doing. Ooh, that makes sense too. Right? Let's put some numbers in. I got this many Newton force acting for this many seconds. Right now, it's a tiny, tiny time interval. Sometimes those time intervals are given in milliseconds, so you have to convert to seconds first. So watch for things like that, possibly. Okay. And this all happens acting on a mass of, well, a baseball is pretty close to this mass, so let's call it that many kilograms. Okay. So what we get out of this, that times that over that. Okay. I'm looking at this many, guys, that many, what's the unit? What meters per second? Yeah, meters per second. Okay, because we're talking about a change in velocity. Change in velocity. That's what delta V is, right? Change in velocity. Right, 42 meters per second. Right. Okay, so I mean, circular answer. You got an answer. Right? But how about an extension question here? Right. What does that mean about the final velocity of the baseball? Okay. Now, if the baseball is just sitting on a tee, then that's a really simple question to answer, right? Because the baseball is sitting on a tee, it starts at rest. You hit it with this force, by the time, bam, now it's moving at that speed. So that would represent the final velocity if it starts on a tee, right? But Right, here's a more interesting question. What if, here, I'm swinging this bat right here. Right, here comes the baseball. Right, it's coming in at, I'm just gonna make something up. Suppose the pitcher pitched the ball at like 20 meters per second. And then, bam, hit it with the bat, and then the ball is gonna rebound back the other way. Right, so, right. What is the final velocity of this baseball? Given all these, let's suppose that all this calculation is exactly how this plays out right here. Right? And I only gave you one new detail, which is that the pitcher pitched the ball at 20 meters per second. What is the final velocity of my baseball headed towards the outfield? 22. 22 meters per second, right? Because here, there's this reversal in direction. Remember, last few days we've been dealing with vector quantities. Isn't it true that delta v, change of velocity, is final velocity minus initial velocity? And how does that play out? I'm looking at, here, I'll just work backwards from the answer. 22 meters per second, it left the bat, minus negative 20 meters per second headed towards. Okay? Don't forget that here, reversal direction. I need a negative sign somewhere. Maybe I should say the pitching velocity was negative, right? Negative left, positive right. There's my 42 meters per second change in velocity. Matches. All right there. Okay, that's it. All right, yeah, so careful about that if you're reversing direction, okay? Which is really common, for collisions, right? If you're hitting something with the bat, it's gonna bonk back the other way. I think there's a question coming up later that involves like somebody like hitting a volleyball, bam, there's a reversal of direction. So you got to be careful about negative signs, right? Okay. And last one, number 11, same premise, hit a ball with the bat, right? But this time I told you what the change in velocity was. So let's say we brought a radar gun to this party and we know the pitching speed and the hitting speed, right? We do exactly kind of what we did here, right? Subtract a negative, right? Blah, 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 right? So that's all already been done, right? I told you the change velocity. Here's the mass of the baseball again. Let's have maybe the same time interval, right? But question would be, what force from the bat set all that into motion in the first place? Which bet you guys can see how this is going to play out. So just like a lot of these questions, we'll still solve it and then think about like extension type questions. So force, again, this is an average force times time interval results in some mass times change in velocity for the baseball. There's your impulse. Right? If I want to, I could say equals delta p. Maybe I should have done that. That's one too, right? Right. So there's impulse. Let's solve this in terms of variables for this average force right here. Average force, right? Okay, so very simply divide the delta t over. Right? So I could say average force on the ball is mass times change of velocity, all divided by the time interval. Okay. Here's one of the things I want you guys to see that, a lot of these, you see numbers, you see equations, you could turn your brain off and just do some algebra and get the answer of whatever, right? But, if you pause along the way and think about some of the implications here, okay? Guys, this should look familiar from, a couple of months ago. F equals m times, guess what is delta v over delta t? What is that? What is the rate change of velocity? Huh? Acceleration, right? Acceleration. Hey, F equals ma. Hey, what is that? Is that Newton's second law of motion right there? Right? A lot of physics teachers teach it this way. They say the impulse formula is basically Newton's second law of motion. You guys see it's just one algebra step away, right? These guys are like next door neighbors. Right? It's good to know, right? I mean, if you memorize one, you basically have the other. Right? All right, so let's do a plug and chug, and then we'll a little bit more about this. Okay. So I gave you the mass of the ball right here, kilograms. Right. I went ahead and told you the full change of velocity, so just plug that in. Right. And the time interval this all happens in. Go down, see what we get. That mass times that change of velocity, all in that time interval. Right. So my numbers worked out. I need this much force. Okay, so that would be Newton's, right? Right, Newton's force. Right, to dot all into motion. Okay. Right. Oh, here's another extension question I have on this one though. Right. Suppose we go to the store, we buy a baseball. Maybe it's kind of a cheap baseball. It's like, okay, well, maybe I'm poor or something, and I got a cheap baseball. And this baseball, maybe it specifies on the package. This baseball, you can go and play with it. It's all fine and good, as long as you don't apply a force more than about 300 newtons. Once you hit like 300 newtons and above, then, well, now all those seams are going to tear apart, and now you're done playing. So if I just hit this baseball, and here's my average force, okay, is this baseball still intact? Remember, it can go up to 300 newtons force, and then after 300 newtons, it's just going to fall apart. Okay, or does this baseball fall apart? Okay, let's see, show of hands, what you guys are thinking. How many guys think that after this particular hit with this bat, the baseball's still okay? Still okay. Okay, go up to 300 newtons, right? How many guys think this baseball fell apart? Fell apart. Yeah, yeah. How'd you know? How'd you know this baseball actually fell apart? It can go up to 300 newtons. What's wrong with that? Ah, that's the average, right? Let's take this back to this graph right here, right? So we just did mass times velocity is force times time interval. That was an average force, right? We're talking about, we were thinking in terms of like this rectangle right here, right? Which tells the correct impulse, right? But more realistically, probably something like this triangle type graph happened, right? The maximum force is probably approximately double that. So it's probably like about, I would say over 400 newtons is probably like an average force. Yeah, I bet the baseball kind of fell apart, right? Somewhere in the middle. Right, like I said. All right, a little consideration there. All right, but that concludes that half page. Any questions on that half page? Is it? Right. Yeah. If you turn this into the grade tray before you leave class today, then I will get that grade in the grade book over the weekend. If you're behind a few or need a few more days, a few more days, that's okay too. Turn in next week. All right, let's switch over to your textbook questions, chapter 6. We'll do as many of these as we can do and get a good head start here. Yeah. All right, number 8. An estimated, force versus time. Look at that, it's force versus time. Right? Yeah, whenever you see force versus time, even if you don't read the premise, you know right away this is going to have something to do with impulse and momentum. Right? The area of that triangle is some kind of momentum delivered, some kind of impulse delivered to something. Right? Or a baseball struck by a bat. Hey, that's even the same story as we've just been working on. Right? From this curve, determine the impulse delivered to the ball. It's the area of the triangle. And the average force exerted on the ball. Okay, so let's knock out both of those. Right? Number 8. Right? Here, this one I'll just use the exact same numbers as they have. So some of these I might change the numbers, but okay. So you guys know impulse, delta P, is the area under force versus time, right? No, I know, I think most of you guys are in calculus. Let me throw some calculus notation at you guys, which some of you guys will be familiar with, right? Area under force versus time. What's that called? It starts with an I? Integral, integration, yeah, right? And you guys know you can use this elongated S-Looking curve for an integral, right? I might write something like this if I was a calculus teacher. Force is a function of time, like a function, right? Multiplied by dt. That dt, the premise is that here, like if you're adding up, if you want the area of the curve, if you learn this in calculus, the way it teaches, like if you divvy this into like a bajillion infinitesimally skinny rectangles, right? Then okay, you have like this dt is kind of what they're okay. So it's kind of fancy calculus notation for just the area in the curve. Right? But for us, isn't that just the area of the triangle, which is 1/2 base height, 1/2 base height, because it's a triangle, right? It's just the area of the triangle, right? So that's all we're gonna do, right? Okay. Okay. So yeah, this is an integral sign. Wait, it has a name. Is it called an integrand or something? Or what's it called? An integrand, is that what it's called? Yeah. And all it means is that you're adding up the area under the curve, or between the curve and the axis. Right? So in this case, the area of that triangle. Yeah. So that's it. Yeah. Area of the triangle. Okay. Okay. So base. This looks like 1.5 units. Oh, guys, what is the unit for the time? It's not seconds. It's what? Milliseconds. So I see 1.5 milliseconds. So should I put in 1.5? Over 1,000 seconds, right? If I want, right, seconds like that, right? And then the height of this thing, the maximum force they listed is 18,000 newtons. 18,000 newtons, right? Newtons times seconds. That's Newton seconds. Same thing as kilogram meter per second. The thousands go away. All good so far. It's 1.5 times 18 on 2. I'm looking at this many. I could call it Newton seconds, right? I could also call it 13.5 kilogram meter per second. Right? Usually I do momentum as kilogram meter per second, right? Mass times velocity. Right? oftentimes when it's an impulse, you'll see it with this alternate unit, but these are identical units, right? And what's the average force? So that was question A. And question B is what's the average force? F average, right? Now, if the maximum force is 18,000 units, and this is a nice triangle, what's the average force? Half of that, right? Yeah, 9,000 newtons, right? 9,000 newtons, because it would just be half of the maximum. Okay. If it was some shape that wasn't a nice geometric triangle, then what you would do is you would take the area, which is this number right here that we just got from part A, and you would divide by the base, right? But that would give you the same thing. Here, let me show you guys that that's true. That should be 13.5 Newton seconds divided by 1.5 milliseconds. So it's 1.5 divided by 1,000 seconds, right? Let's see if that's true. What's 13.5 divided by 1.5 on 1,000? Yeah, this is the same thing. 9,000 newtons. Okay, number 9, a 0.28 kilogram volleyball. Should probably Google this later. The honors students have a 0.24 kilogram volleyball. I don't know how. Okay. What is the massive volleyball? Approaches a player horizontally with a speed of 15 meters per second. I already kind of forewarned you guys earlier today, right? That when you're hitting a volleyball, it's going to rebound, it's going to change direction. So notice they're using the word speed rather than velocity, right? So maybe they're kind of trying to hide a negative sign somewhere. Let's see if you can catch on to that, right? The player strikes the ball with their fist, causes the ball to move the opposite direction with a speed of 22 meters per second. Again, like if your brain was turned off and you're just like looking at numbers, you might forget that there's a negative sign somewhere here that they didn't actually give you, right? It's opposite direction. But impulse delivered on the ball, if the player's in contact with the ball, for this time interval, what's the magnitude of the force? Okay. So, 9. Impulse. I could do mass times change in velocity. I think is good for part A, right, which is mass times v final minus v initial. It might help to spell it out like that, right? Less likely to make a mistake, right? So we got 0.28 kilogram ball multiplied by, okay, went to 22 meters per second. Let me say minus a negative 15 meters per second. Okay, right. So minus a negative, so that same thing as plus. Right. 0.20 kilogram. Right. Looks like that volleyball is what, almost twice the mass of a baseball. Right, 22 plus 15. I'm looking at this many. I could call it kilogram meter per second. You could also call that Newton seconds. Right? And if this was a multiple choice answer on an AP exam, they might even round that to like 10 Newton seconds or 10.4 Newton seconds, something like that. Right. There we go. Got an impulse. Right. Question B, what's the average force? Right. So average force, could that be change of momentum per time interval? Right. Okay. Like but backtrack to this poster right here. Right. Average force, there's your change of momentum, your impulse, divided by that time interval. That looks exactly like that, right? Okay. Momentum is mass times change of velocity. That would take you back to Newton's second law of motion. Okay, so it's all kind of in there. Okay. So we have this right here, all divided by the given time interval, which was, they listed it in seconds. They said this many seconds, right? They could have said 60 milliseconds and made you convert that. Right, so take that impulse divided by that time. Okay, so I'm getting this number on my screen. Okay, I'll round a little bit, maybe something like that. Okay. You guys, what's the unit on that number? Newtons. There you go. Right. Oh, hey, look at it, because Newton seconds divided by seconds gives you newtons, which would quantify a force. All right, are we good? Right, number 15. Force versus time is shown. Okay, yeah, so force versus time, the first same thing is, okay, this is probably going to be something to do with the transfer of momentum. Right, let's do it here. Oh, find the impulse. Yep, that's just the area of that trapezoid. So the rectangle plus the triangle. And then the final velocity of the object if it is initially at rest, right? And there's an and so it's like I got a part of the question, whatever that was. So 15, the impulse delta p, let's use that fancy notation, the integral of force is a function of time for the time interval, I guess from 0 to 5 seconds if you like, right? Time equals 0 seconds to time equals 5 seconds. So the rectangle plus the triangle, rectangle plus triangle, areas of those things, right? So I got base times height, that's 3 seconds at 2 newtons plus, okay, and triangle is 1/2 base height, right? So the base is 2 seconds and the height is 2 newtons, right? So it's what, 6 plus 2? 6 plus 2, is that 8? Is that right? Is that 8 units? It's about 2, I'm sorry. Yeah, right. Like 8 Newton seconds of impulse. Right, and the final velocity, if it started from rest. Okay? So delta P, or change in momentum of your impulse, is mass times change in velocity. Right? Now change of velocity is final minus initial velocity. If it started at rest, initial velocity is 0, so the change of velocity would tell you the final velocity. Right? So I can say delta V is just impulse divided by mass. That's my delta P divided by my mass. Okay? So we're looking at 8 Newton seconds acting on, what's the mass of the object? 1.5 kilogram. Whatever that comes out to. That'd be meter per second. Okay. So, but that really solves for the change in velocity. But if it started at rest, that would also be the final velocity, kind of like the baseball that starts on a tee. Right? Whack it with the bat. All right, are we good? All right, so that's this number 8, number 15 are kind of similar. Okay. All right, number 18. What's this? A so many kilogram steel ball strikes and boing bounces off a wall. A massive wall. Right? The wall is so massive that it basically doesn't move. Right? It's like infinity times the mass. Okay. At some speed at some angle. Right? It bounces off the wall with the same speed and angle. Okay, so whatever speed going in, same speed out, and then same angle, same angle. Right? Guys, if it did not change its speed, then what do you know about the type of collision with the wall? Perfectly elastic. Yeah, right. Because the kinetic energy is the same after compared to before. Yes, this had to be perfectly elastic. Right? Another side detail here is, now this is kind of going to get into next month content, but if that's really true, if it has the same translational speed, the only way for that to happen is that none of the energy also went into making it rotate. So there was like no torque on the wall to make it rotate. So that could only happen if it was a frictionless wall, right? Or you might say, well, we're just going to approximate this as pretty dang close to being true, and there's like negligible effects to blah, 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 right? But if this is strictly true, then the ball isn't even spinning after, so there's like no frictional force. Okay, so those are just side thoughts that might factor into some of these questions down the line. Right? If the ball is in contact with the wall for 0.2 seconds, so a fifth of a second, again, a lot of these collisions, tiny time intervals, makes sense, though, right? What is the average force? The wall on the ball. I'm pretty sure I have actually asked you guys this question in the past, right? Maybe in a pick-on quiz question, because you guys could solve this in the past using Newton's second law of motion. Okay? But I saw this week and today that this impulse question is just one step away from Newton's second law anyway. So yeah, you can solve this before, you can solve it now. Right, 18. Right. I'm gonna change some numbers on this one. I probably should have done that for some of the other questions too. Oh, get a phone call. Let's do pause on this video. All right, recording resume. All right, so I'll keep the same premise about it being perfectly elastic, right? Okay. But I'm gonna change some things. So I got a wall. Right. I'll have a normal line. I'll keep the same angle. How about that? Same angle. So, right. So it's like coming this way, then bam, right, collision with the wall, and boing, bounces out that way. Right. they said this is 60 degrees, so I'll just keep that at 60 degrees. Right, so theta equals 60 degrees. Right, so all that. Right, let's have the mass of the ball be, how about 0.15 kilograms for the notes? Right, so maybe I got a baseball going on. Let's have the speed be, let's see what they, right, I'll have like 25 meter per second. About that, 25 meter per second. And is that all I need? I think it's, time interval, right? So let's have a delta t, so a time interval of about 0.10 seconds of that. Right. So there's enough info there we can solve for the force from the wall. Right. All right. So remember, force is a vector, momentum is a vector, impulse is a vector, velocity is a vector. Right? So directions matter. This is a two-dimensional concept question, right? There's an x-axis and a y-axis. Right? Now, if you just track the ball what's going along the y-axis, nothing ever actually changes, right? The ball doesn't speed up or slow down or ever change what it's doing in the y direction. Along the x direction, it completely reverses direction. Right? It's like, well, same speed after a bit, but complete reversal of direction, right? So I'm really interested in what's going on the x direction, and the force from the wall, right, is actually a normal force, which means, like by definition, it's in the word, right, has to be perpendicular to the surface, which is also only in the x direction. I'm going to break this velocity vector into components. And then by symmetry, I know this one's doing the same story on that side. Okay. So go ahead and do that too. Bam. Bam. Like break it into components, right? Dash in my components, right? I do need to go back and fix a lot of those pre-made solutions that I made a few years ago because you know, I used to draw things a little bit different. But if you guys know, if there's an actual vector, make it solid. It's let me pause that. All right, recording to resume. All right, and then if you want the components, go ahead and dash those. Right, so I got these velocities going on. Remember, in the y direction, nothing's actually changing. So I really care about, it was going to the left here, it's going to the right here. I care about the change of velocity in the x direction. So what is this component of velocity right here? That is, I'm going to use my numbers. I got 25 meters per second is the full velocity, right? Times, is that sine or cosine of 60 degrees? Sine of 60 degrees, right? Because it's opposite of the lifted angle. So let's see what that comes out to. Right, it's like this many meter per second. Right, so I'm keeping a ridiculous amount of precision, but maybe it's a good idea to save my rounding for the very end. Okay. So I got that. So over here. So what is my change in velocity? And of course, it would just be in the x direction. Specify that. Okay. Is that okay? I bet it leaves 21 point something meters per second here, and it started going like negative that same number in the opposite direction. So it's like 21.65 meter per second minus a negative 21.65 meter per second. Right? Wouldn't that be the change in velocity in the x direction? So that times 2. Right? Looking at like this many meter per second is the change in velocity. The change in velocity on the x direction. Okay. So we got that. All right. The question was, what's the force? What's the average force? Can I put that? Might be able to put that. But we'll see. So I can put that on the page here. Okay. So I know that average. Notice they said average force, right? Times time interval is equal to mass times change of velocity. Or if you like, you can do the Newton's second law of motion version of this. Average force is equal to m times delta v on delta t. Okay. That's kind of like Newton's second law of motion. Well, here. I think I can finish this off down here. Okay. So the average force from the wall is, I got the mass of the ball, kilograms. Okay. I got the change in velocity because I just did some trigonometry and subtracted a negative, right? Got this many meter per second change in velocity. And this all happened in the given time interval. If you had like a slow motion camera, you could kind of determine what that was. Okay. Let's put it all together. Okay. And it depends what kind of wall too. Like if the wall is like cushioned, if it's a longer time interval. If it's like a steel wall that's pointing, that's a lot smaller. Times 3 divided by 1. Right. So my made up numbers, I'm getting about this many newtons of force from wall. Newtons of force. Yeah. Yeah. That pretty good right there? For guys too? Okay, so while you guys are finishing on that one, here's maybe some extension ideas on this one, right? It's nice that they gave us a wall rather than a floor. And I think when I gave you this question before, I also gave you a wall rather than a floor. Because if it's a wall, then all that's going on is pretty much exactly what we just did here. If you're dealing with a floor, then you also have to consider the weight of the ball, which changes a bit, right? And what I listed here as an average force, you'd have to consider would be an average net force. And you have to say if the ball is bouncing off a floor, then this average net force would be the difference in the normal force from the floor pushing up and the weight pulling down. So the actual normal force from the floor would be even greater than this because you have to tag on the weight of the ball. Right? So it's just like one more step of complication. Right? But the ball is kind of nice because get through all that. Okay. All right, guys, ready for number 19? 19. The front 1.2 meter of a 1,400 kilogram car, I might change the numbers for the notes, right? Designed as a crumple zone that collapses to absorb the shock during a collision. Oh yeah, right. So like car crashes, if you're designing cars one day or you're doing like dummy car crashes, I bet it's all this unit right here that we're doing, right? Momentum, impulse. The car goes 25 meters per second, which is about 60 miles an hour, but stops uniformly in 1.2 meters. Okay. Oh, and notice it says stops uniformly. That's one of these side details that would actually be an important detail if you're designing cars and you want to make them crash safely. Right? How long does the collision last? What is the magnitude of the average force on the car? What's the acceleration of the car? Express the acceleration. Oh, as multiple of the acceleration due to gravity. Like how many G's would you feel, right? So let's get a picture going. Number 19. Okay. So look at this car going. Okay, I'm gonna draw a more realistic car than I normally do. And okay, so we got our crash dummy in here. Right, so you guys are designing cars one day, right? And you're driving these cars, you just plow them into this wall. So pow, 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 right? Yeah, and you're getting all kind of data from this. Right? Now, if you made your car like completely rigid steel, like this car is indestructible, then this car would boom come to a stop like immediately, wouldn't it? So the time interval of that crash would be really small. Let's see what would happen to. What's the first question? Oh, well, okay. First question is how long does the car last? The second question is what's the force on the car? Right? But yeah, let's kind of jump to Newton's second law version of the impulse formula, which is average force is mass times change in velocity over change in time, right? And let's use this equation to like kind of guide our thinking as to what it would mean if the car was completely rigid, right? Well, the mass of the car is whatever it is. The change in velocity of the car would be no different because you're letting it go whatever speed and it's going to go to zero speed. So the change in velocity just is what it is, right? But that time of stopping would be tiny, tiny, tiny. This what happens to a fraction if you divide by a tiny number. It blows up huge. There'd be a huge force on the car, and you as a driver, that would be really jarring, right? So you want the car to like give some amount, but you don't want the car to be like made out of cardboard, because if it's made out of cardboard, what happens, right? Is that it just keeps going, keeps going, keeps going, and then it hardly slows down at all until suddenly it does slow down all at once, and you run into kind of the exact same scenario. Is you run into like a huge force, right? Ideally, what you want is for this car to slow down uniformly. So that word uniformly is doing a lot of heavy lifting on this question. It's doing a lot of protection to the driver, right? Because if it slows down uniformly, what's going on is that collision where you can't change anything in the numerator, right? But that denominator, you're blowing it bigger. You're making that collision last for a longer time interval. Okay. Oh, let me see if actually I think I do here have a picture for you guys. Won't probably finish this in class, but right, that right there. You guys ever seen these out on the highway? Right, attenuator. So suppose you're driving, you're either distracted or sleepy or something, right? The car starts to kind of drift off the road. Ooh, look at that concrete barrier right there. Concrete barrier. If you make a mistake driving, you don't want to slam into that concrete barrier. Right? But if you slam into this attenuator, that's a lot safer, right? You're a lot more likely to walk away from that crash, right? Because look what it does. It extends both the distance and the time of that collision. So the acceleration is a lot less, the force is a lot less, right? So of course you wouldn't want to hit either if you didn't have to, but better to have there than not. Okay. So question A is how long does the collision last? That sounds kinematic. I think we're gonna have to go back to old kinematic days to answer how long it lasts, and maybe also get the acceleration might be helpful. Right, so I want to break out the kinematic equations for this one. Right, so I'm thinking this right here. Right, now this is where about the bell was ringing in my last AP class, and yeah, we got about a minute left class too. Right, so maybe I'll leave that right there, and next time we come back to these textbook questions, we'll pick up the story from there. Okay. So it's gonna be a kinematic feature of this. Okay. All right, but yeah, I hope you guys have a good 3-day weekend, Veterans Day weekend, and yeah, look for a rocket launch around 8:28. Oh yeah.